The second talk in our seminar series, and we are fortunate to have Dr. Lynn Wilson with us. Dr. Lynn graduated from St. John's University in 2005 with a BA in physics and went on to the University of Minnesota to work with Cynthia Cattle. He defended his dissertation entitled The Microphysics of Collisionless Shocks in September 2010 and started working at NASA Goddard Space Flight Center about a week later, where he's been ever since. His graduate work was primarily using WIN spacecraft data, so he was chosen as the deputy project scientist for WIN by the then project scientist Adam Sabo in 2012. He took over as the WIN project scientist in July 2016 and continues in this role today. He has worked on multiple things, from collisionless shocks to radiation belt dynamics, and is an active participant in APS, AGU, GEM, and SHINE conferences. So welcome, Lynn, and now I hand over the baton to you.
All right, thank you. As you said, I'm Lynn Wilson, and I was asked to talk about the solar wind, and so I'm going to try to present an overview of things, but I'm going to explain some of the things I want to go through here. So I'm going to start off with some jargon and basics just to get everyone on the same page. I'm going to talk about the solar wind and discuss how there are basically two types of solar wind, fast and slow, and then go through really superficially some of the interplanetary magnetic field geometry, talk about some temperature-dependent solar wind properties so we understand the nuances of the kinetic gas we're talking about, because it's not a fluid or anything like that. And then I'll go through and again, kind of superficially go through the different solar wind transients. And these are co-rotating interaction regions, stream interaction regions, coronal mass ejections, solar energetic particle events, things like this. And a little backstory. So when I was doing some of the literature review for this talk, I was digging into this, and I knew there was a bunch of nuance in any of these solar wind transient fields, but I started to realize that there was much more than I had anticipated, and I was kind of surprised at how much there was. So for instance, solar SEPs, there's a large fraction of the community, or a sizable part of the community, argues about different types of sources for these things. Are they solar flares? Are they coronal mass ejections? Are they reconnection jets in the corona? And there's some parts that say that shocks don't generate any of these. Some say they do, and I was really kind of amazed at the nuance in the literature. So anyways, yeah. So let's get started. So the solar wind is not a fluid in the typical sense that where you think of it's a substance that smoothly and continually deforms under shear stress. It's more like a non-equilibrium kinetic gas. So the solar wind is an ionized gas, so the electrons are stripped from the ions, and it's roughly quasi-neutral, so that there's roughly equivalent electrons to the number of ion particles. But I'm emphasizing this because the different populations behave differently under different conditions. They're not all behaving as one medium like you might expect from the Earth's atmosphere. And at STP, all the particles are roughly at the same temperature, whereas in the solar wind, each of the different populations, and there are many populations, can have completely different temperatures, different drift speeds, different anisotropies, different skewnesses, kurtoses. So they all behave rather differently, and they respond differently to different sources and different events in the solar wind. But the bottom down here, just listing off some of the different parameters, so like the plasma and cyclotron frequency, which we all know and love, the thermal speed, the Alfvén speed, and the plasma beta, the Debye length, all these quantities we all know. So yeah, so the different populations, they don't need to have the same temperature. In fact, they often do not have the same temperature. And it's not just, say, ions and electrons have different temperature. It's the populations within each species. So the electrons, there's core, halo, and strahl in the solar wind. They often don't have the same temperature. So even the subpopulations are different. And they also don't have, they're not isotropic. So both of these things show that the plasma is not in equilibrium. There's also a rather ubiquitous presence of heat fluxes in both the ions and the electrons more so than the ions, and it's typically carried by the Stroll part of the electron distribution. And so because of this, it's a non-equilibrium kinetic gas. It's not in equilibrium, both thermal or thermodynamic. And that's kind of important for understanding the dynamics and evolution of the solar wind. There's even been recent stuff that we think we might have found some evidence of inelastic collisions, which was kind of exciting. So the sources of the types of solar wind. So many years ago, for some of us, the Ulysses spacecraft went out to Jupiter, used Jupiter to change its angular momentum. So it went out of the plane of the ecliptic and went nearly over the poles of the sun. And so it took several years for this orbit to occur. So you can see in the left-hand panel there, the first orbit was during solar minima. And you can see that near the poles, the solar wind speed, which is indicated by the radial magnitude of these lines away from the origin, is higher at the poles than it is near the equator. And during the solar maxima, which is in the second orbit, it's all over the place. It jumps all over the place. And so it has led people to start to think about the source of the different types of solar wind. So the fast solar wind, when it's above 500 kilometers a second, give or take, and the slow solar wind, which is below, the fast being related to open field lines in the corona, and the slow being related to these streamer belts. This is called a helmet streamer. And I think the name helmet comes from the shape of this on the chronographs that you view, and it looks kind of like a Prussian helmet, I think. And someone that's more familiar with the history might be able to correct me on that. But the overall point is that during solar maxima, there's closed and open field lines all over at all latitudes of the sun, whereas at solar minima, the open field lines are mostly at the higher latitudes. And so you get these different speeds coming from different regions, but it's not just the speeds. The speed is different, but there's also different things that change. So the temperatures are different, the densities are different, and the different types of winds are also known to have different elemental abundances. So the heavy ions change in the different winds. And this is also interesting because as people started to look into this and investigate it more, they started to realize that just using the speed as a cutoff wasn't sufficient. There were times where you were at lower speeds, but you had elemental abundances and temperatures that were consistent with the higher speed solar wind. And so it's not just entirely dependent on the speed. So there's a lot of nuance involved in this, and there's a lot of active work going on. The other thing that was kind of interesting is that the composition depends on the first ionization potential for the slow solar wind, but not the fast. So I thought that was kind of an interesting point. But the other thing too that's interesting to note is that we're sitting at 1 AU, which is roughly at this ring here on this Enlil simulation plot. It's just a snapshot of an Enlil simulation for March 26, 2012. The solar wind, the IMF, the interplanetary magnetic field, can intersect with the Earth at multiple different angles, and that changes the dynamics of the magnetosphere, because you can have radial fields where you can have the solar wind interplanetary magnetic field is impinging directly on the nose of the magnetosphere, or if it's impinging on the flanks, and that changes the magnetic activity in the magnetosphere, as Joe mentioned earlier in last week's talk. And so the field geometry matters a great deal when discussing the solar wind, and it matters in regards to different types of transients and connectivity, and which sides of the sun we expect to see transient events affect the Earth. So if we go into the fast versus the slow wind, and we talk about the temperature-dependent parameters, I'm going to talk about something I worked on a few years ago, specifically on the using 10 years of wind data. And I went really simply and just used the speed because I didn't have the composition data handy. So I just used the speed as the separation between fast and slow. But as I said earlier, that isn't always a sufficient distinguishing line. So the first thing to note is that when you look at say like the electron density, the proton, and the alphas, the slow solar wind tends to be denser than the fast solar wind, and so there are more particles per cubic centimeter in those regions. And the alpha particle abundances tend to be higher in the fast solar wind. And so the composition ratios change just slightly in the fast versus the slow. The temperatures are, in general, higher during fast solar wind. So it doesn't matter whether it's electrons, protons, or alphas, they tend to be higher. The ions tend to be, the difference between slow and fast solar wind for the ions is much larger than it is for the electrons. The electrons don't increase by much, but the ions increase significantly. The other thing that's kind of neat is that the fast solar wind is more anisotropic. And I'll get to this later. It's related to the collisionality and other effects that happen between the sun and the earth. But the plasma populations are rather distinctly different between these two types of solar wind. The plasma betas too are higher for the electrons in slow solar wind, but they're higher for the ions in fast solar wind, and this is related to the temperature being so much larger for the ions, because the density is smaller during these times. And if we look at the temperature ratios, we talk about the electron to proton and alpha, and then the alpha to proton ratios. So the electron, as I said before, the electron temperature doesn't change much between fast and slow. It is slightly higher in the fast wind, but it doesn't change anywhere near as much as the ion parameters. And so during slow solar wind, the electron to ion temperatures tend to be higher. But the interesting thing is that if you go between fast and slow solar wind, the alpha temperatures jump way more than the protons. So the ratio of the two is significantly higher for the fast solar wind. So so I was saying earlier that part of the reason for these differences is related to collisionality. So if imagine if you're in the slow solar wind, you have a lot more time to get from point A to point B. And so any effect that takes some unit time to occur, you have more opportunities for that event to occur. And conversely, with the fast solar wind, you have fewer. And if the energies are higher in the fast solar wind, then you can see in the collision rate here, it's run over roughly proportional to 1 over the speed of the particle cubed, of the incident particle cubed. So and this is the root mean square of the thermal speeds of the two populations that are colliding, S and S prime. But if you have a higher energy particle, your collision rate should drop off. And so the collision, it's the combination of having less time to collide and the particles having more energy, thus there are fewer opportunities for collisions. But if we look at the collision rates here, I should mention, I also did a kind of a simple estimate of the collision rate between the particles in an ion acoustic wave. And I did this just because the ion acoustic wave has this nice, convenient analytical expression for quasi-linear theory. And because we see ion acoustic waves all over in the solar wind. By ion acoustic wave, I mean the electrostatic version of the mode, the high frequency part, not the slow MHD mode. And so we can compare the collision rates between fast and slow solar wind. So we look at the number of collisions per day. And so the ion acoustic doesn't really change because it's basically depends on the density. So it's just a slightly higher during fast solar wind than slow. But the electron-electron collision rates are higher, and so are the electron-protons during slow solar wind. And then basically the rest of the particle populations that are colliding, so the proton, alpha, proton, alpha, are all also higher. But pay attention here, this is number per day. The fastest rates here are the electron, and at the high end, 75th percentile, we're still only 1.4 collisions per day. And this is assuming 90-degree deflections and things like this. So it's a very specific idealized case, but again, the collision rates here are at best 1 per day. And so if you look at this, for 400 something kilometer per second solar wind, it takes about 4 days to get to the Earth. So you might have 4 or 5 collisions for any given particle on its way to the Earth. So I'm more interested in why there's any evidence of collisionality in the solar wind rather than whether or not it occurs. I'm kind of surprised that there is any evidence of collisionality, because we do see collision dependent parameters in the solar wind. We see dependencies on the collision rates in a lot of different things. And it always kind of surprises me, because if the collision rates are this low, yet even for a very conservative estimate for the ion acoustic waves, you're 60 to 50 times higher in the collision rate. So you basically interact with one ion acoustic wave, and you have to wait 40 days before you have the same effect washed out by the binary Coulomb collisions. So I'm always kind of amazed whenever we find evidence of collisionality in the solar wind, and it makes me curious if it's a remnant of the corona and we're just seeing that and it hasn't evolved much, or if it actually is collisional in some sense. So we can also look at the histograms of these different populations. You look at the temperatures for the first columns, the electrons, the second's the protons, the third column's the alpha particles. The different rows are the different types of solar wind. So this is all data. This is the fast solar wind and slow solar wind. And I made a mistake in making these histograms. I didn't actually normalize by the bin size, so that it's inappropriately weighted a little more towards the larger bin sizes. But the distributions are basically show that the vertical lines are the medians for the different components. So there's total, parallel, and perpendicular temperatures. And so the electrons don't really change much between the fast and slow wind. You can see that here. The median value doesn't really jump around. But for the protons, not only do the median values vary quite significantly, the shape of the distribution is very different. It's almost like there's two different populations here. The same thing for the alphas. They're bimodal in both the fast and slow solar wind, but the shape of the bimodal is very different. And so it's really kind of interesting why the different populations behave this way. And when you look at the temperature ratios, again, because the electron temperatures don't vary much, the shapes you're seeing in these distributions are largely driven by the population with which you're comparing. So the electrons, the protons, you see the different changes here in the shape. And this, again, the shape is largely driven by the proton population. Same thing with the electron to alpha, and you can see the bimodal peaks here, the two different peaks, and that's mostly coming from the slow solar wind. Whereas the alpha to proton, this is kind of neat. So there's one peak here that's slightly above 1.0, and if it were at 1.0, they would be in thermal equilibrium, because it'd be T alpha equals T proton. And there's another peak here that's not at, what is this, 2, 3, 4, 5. It's actually around between 5 and 6. It's not at 4, which would be it'd be equal mass partition. So it'd be like if you had equal thermal speeds for the two populations. It's actually above that. It's around between 5 and 6. And again, this has kind of been a source of great interest and confusion in the community, because it begs the question, so why is the peak not at 1 and why is the peak not at 4 when you have this bimodal distribution? Because there are reasons why you'd expect the thermal speeds to equilibrate and why you'd expect the temperatures to equilibrate, but they actually deviate from each. And so the argument has been for quite a while that one of the main reasons for this is likely due to resonance with things like ion cyclotron waves and other modes in the solar wind. So we look at the betas as well. You can see that the betas are kind of interesting because there's such a broad range of values. So the median value for the electron sits between 1 and 2 basically, but you can see it extends down to 0.01 and goes well over 100. And if you look at the protons, the same thing, but the protons and the alphas go even higher. And so the protons go even higher and the alphas go even lower, because the alphas have a much lower density. So that's why they're shifted to the left here. But there's a rather broad range of parameter space for the different plasma betas in the solar wind, and it's not just the beta is 1 or 0.1. There's quite a few values at even higher ranges. So it's something to consider when thinking about the different parameters you put into your simulation. So let's go on to the solar wind transient. So I said before that there's some interesting nuances here. So there's SIR is a stream interaction, CIR is a co-rotating interaction region, and that just means the difference between SIR and CIR is basically the CIR has to, the stream interaction region has to make it around the sun more than once, so more than one Carrington rotation for it to be called a CIR. Otherwise, if the spacecraft at 1 AU only sees it once, then they just call it an SIR. And again, because of the nuance, some of the experts that work on this are probably probably squirming in their seats, wondering, thinking like, oh, there's more to it, there's more to it. And if there is, please correct me at the end of the talk. CMEs, coronal mass ejections, the ICMEs, interplanetary coronal mass ejection, these are driven by bursts of plasma coming from the sun. So things like magnetic clouds, flux ropes, prominences, eruptions, things like this. And the type of driver or the obstacle, the magnetic obstacle that causes these things is also a source of interest in a tremendous amount of research, because it initially was thought that, okay, you have a prominence or some sort of flux tube that erupts from the sun and it just moves out into the solar wind, but the ends of it stay connected to the sun, or they reconnect entirely and it becomes an isolated bubble that moves out. But if we look into this a little more, we're starting to find that there's a lot more to this, and there are different types of pistons, different types of magnetic obstacles that drive these things that are parts of what we call ICMEs. And so magnetic clouds is one type, and there's what we see there's a increase in the magnitude of the field. There's a smooth and slow rotation in the magnetic field that can last anywhere from hours to days. There's an increase in the proton temperature, and the flux ropes are similar to the magnetic cloud, and there's some nuanced differences between them. And again, like I said earlier, if you read into this, the number of different kind of nitpicky details about each of these issues is rather significant, and I didn't want to bury everyone with a laundry list of different differences between the different zoologies here. And then SEPs is solar energetic particles, and Don Reams wrote a book that has a lot of background on this, and Ian Richardson has some good papers on this, and this is a huge field of research, so there's a whole pile of papers that you can go through if you're really interested in this. So just to give you kind of a cartoon picture of what's going on, simulation picture of what's going on, this is N-little simulation. Again, here's a CME coming off, and you can see this is R squared N, so it's the density of the plasma, and here's a stream interaction region, which is what I was talking about. And if this thing makes it all the way around the sun as the sun rotates, and you're sitting at Earth over here, if this makes it around again twice, then it becomes a CIR. So it has to rotate twice. And so what are coronal mass ejections? Well, first of the largest explosions in the solar system, they release upwards of a trillion stone league squared per jiffy squared in the standard units, right? So actually, when I was in grad school, I used to put these kind of goofy units in to see if people were paying attention. I always thought it was kind of fun, but the real thing is that anytime one of these goes off, it's couple million times the total world energy consumption per year. So these are extremely energetic events for our solar system. So the fast and slow stream interactions, they really develop because there's as I was saying earlier, there's the different source regions in the sun. So there's the open coronal holes, and then there's the helmet streamers. And while this is under debate and there's some nuance behind this, the basic idea is that the coronal holes tend to have faster solar wind flowing from them, and the streamers tend to have slower. And so as the sun rotates, the sun is constantly sending out jets of plasma, and the part that sits right above the streamer will see slower solar wind, and the part that sits right above the hole will see faster. And so the faster eventually catches up to the slower solar wind and creates this compression region and if it pushes hard enough and it's fast enough, you can actually develop a shock on the leading edge. And these things wind up as the solar wind propagates out towards 1 AU and beyond. And in fact, by the time you get out to the heliopause, out at the edge of the heliosphere, or not the heliopause, the termination shock at the edge of the heliosphere, these things are all piled up on top of each other, and it's one CIR after another. And the shocks that they form tend to form after 1 AU. They tend to still be in their steepening phase by the time they get to 1 AU, but they can still form at 1 AU. It's just more often you see them at further out. So the interesting thing as well is Joe Borofsky, the speaker last week, and Mick Denton did this nice paper in 2006 where they actually compare the different types of geomagnetic storms. Since we're curious about the magnetosphere and the system that interacts with the solar wind, the CIRs and SIRs drive not only different types of storms, they drive different strength storms and different effects on the magnetosphere, different type responses from the radiation belts, different auroral responses than when you compare them to, say, ICMEs. And so it's an active area of research and people are really interested in this. There's also some differences in elemental abundances when you look at shock waves generated by SIRs versus CMEs. That's also kind of interesting. So the next thing is solar flares. So it's just a massive localized enhancement in UV and X-ray light. And so you have some physical space on the sun that lights up, and in this case, it's this region here. See a bright intensification, and it's relatively localized on the entire solar disk. And these things are ridiculously energetic. They're releasing the equivalent of combusting 1 trillion to 500 or 100,000 trillion gallons of gas. It's a tremendous amount of energy, and it happens in a matter of seconds or minutes. And and when this happens, they can send out large bursts of energetic particles. They can change the ionosphere and that ionization of the upper atmosphere, which affects GPS and location services, and it can even affect communication satellites as well. So these are also interesting and worth a lot of study. Let's see if I can get it to go to the next slide. There. So the thing that we also want to worry about is, even though we have these interplanetary coronal mass ejections and CIRs, SIRs coming out, they don't always form shocks, but when they do, the shocks themselves tend to cause a bunch of problems for the magnetosphere because they accelerate particles, they change the dynamics of the Earth's bow shock and magnetosphere response when they impact, and in some cases they generate rapid responses from the radiation belts, either depleting them or filling them, and they can generate extremely energetic electrons in the radiation belts on the order of several MeV. So these things are very important, and lots of customers, so the military and the commercial side, are very interested in this type of thing, because if you have a geosynchronous satellite or a satellite in different parts of the orbit around the Earth, if you're expecting to receive lethal doses of radiation every few seconds because you have a bunch of shocks coming through, that's something you want to know so you can change the design of your satellite. So it's a very important thing to care about. So this one was one that kind of surprised me. So energetic particles, so there's a bunch of different types. There's SEPs, ESPs, and I'm not going to go into the zoology and the naming of different particles, but I was kind of amazed at the amount of nuance and the differences in the different groups of people arguing about these topics. And so there's two basic types that people have named of SEPs: gradual and impulsive. Gradual, their names kind of imply what you observe in the flux versus time profiles. Gradual is there's a slower onset and longer duration decay, and the impulsive is abrupt onset and a shorter duration of the decay. But there's a whole mountain of nuance involved in this. Like, the graduals are likely due to CME shocks, but there's groups of people that say that CME shocks don't accelerate these particles, so that can't be it. The other problem is that if it is a shock generating these, then you have to worry about transport. So as the particles stream away from the sun, they interact with the background plasma that's in between the sun and the Earth. And so any direct acceleration signatures you might expect to see in the flux profiles are washed out or obscured by transport effects, so diffusion and things like this. The other thing that's interesting is the difference in non-thermal abundance variations between gradual and impulsive events. And so the impulsive events sometimes are associated with solar flares, but there's also people that argue they can't be due to solar flares because we don't associate them with gamma ray lines. We never observe elements associated with nuclear interactions like lithium, beryllium, and boron. There's a 1,000-fold increase in helium-3 to helium-4 during these types of events, but helium-3 is not a nuclear constituent, or nuclear reactant. So there's a bunch of interesting discussions about this. And the other thing too is that if a CME generates one of these types of events, the width and the speed of the CME are critical. So the wider CMEs tend to generate the gradual events, and the wider they are, the bigger the intensities can increase. And that's partly due to the fact that as you have a larger and larger surface area or a surface, the particles can have a longer connection time as they skip across the thing before exiting or escaping. And the longer the connection time, the more energy they can gain for various reasons related to shock drift and diffusive shock acceleration. But if a CME-like structure generates an impulsive event, they're generally smaller in size, they're smaller in magnitude, magnetic field magnitude and things like this. They're slower and they tend to be very narrow. So which begs the question is if the impulsive event coming from such a narrow CME is due to kind of a fire hose type thing where you're either in the spray field or you're not. So again, there's a whole mountain of nuance, and the two papers I have listed at the bottom actually go into a lot of these details much better than I'm listing here. But to show you some examples here, so this was kind of a fun shock that I've looked at in several papers. On April 6, 2000, the shock happens at the red line here. So this is the magnetic field. Here's the components of the magnetic field, and what you're seeing below here are the electron distribution, or the electron pitch angle distributions at different pitch angles. So it's the flux versus time. This is roughly the parallel direction. This is the perpendicular, and this is the anti-parallel direction. You can see the shape, the time flux versus time profiles are very different depending on the pitch angle you're looking at. These are for 27 to 500 keV electrons. I normalize these by a certain amount of time so you can see the relative change. So the gray shaded region is what is the time period I used as the kind of the background of the averaging point, and then everything after that is relative to it. You can see that indeed the highest energies change the most compared to this averaging period, which is really kind of interesting. But there's this abrupt onset, which is in this direction is likely due to X-rays contaminating the data, but the other directions it's not present. You can see that there's a time lag depending on the different pitch angles, and that's partly due to light gets here faster than electrons. So but you can see the time flux versus time profiles. We look at the same shock, but with the ions from 70 keV to 7 MeV. Again, you see the different pitch angles have different flux versus time profiles. There's this nice smooth slow onset, and there's a difference in the peak right at the shock depending on whether it's parallel or perpendicular or anti-parallel. And this would be something similar to what I would call a gradual event. But again, based on my reading of the SEP stuff, I'm willing to bet if there is an SEP expert online, they will argue with me about that. But yeah, this is kind of what they look like, and you can see that this is showing 3 or 4 orders of magnitude change in some of these parameters. So you're going from say 1 to 1,000 or more. So the abrupt increase and the large increase in fluxes is rather impressive in some of these cases. So that this is concerning to the magnetosphere folks because it affects the dynamics of the magnetosphere, and it affects satellites and numerous other things in space. So these are the types of things that people are curious about. The other thing that's really weird about these SEPs is, so this is taken from the ACE News website. So they noticed on this day, August 18th, 2010, there was a solar flare, and the solar flare happened along this green line. Basically, there was a little spot on the sun that erupted in UV X-ray light. The Messenger spacecraft, which was orbiting Mercury before they decommissioned it and crashed in, observed energetic, I think these are protons, onset right here. So you see the orange line in the flux versus time profile over here. Oh, these are electrons, sorry. And then stereo A, there's a slight delay, which is just the time of flight effect. So that just takes electrons a few minutes to get there. So they run basically along the magnetic field and get out to stereo A. And this is all on this side. Now electrons generally are field aligned, so you wouldn't expect to see them anywhere else. But on the opposite side of the sun, there was still an onset, quite a bit after, but there was an onset in the electron seen at stereo B. And at ACE, at Earth, there was an onset, and it was very close in time to the onset at stereo A. And so that once stereo launched and they got far enough apart that the community could start seeing this, it became a huge question, because how can you get that much cross-field diffusion that quickly? Because the particles are streaming in all different directions to get to the different satellites at different locations. They have to be skipping across the field lines to do this. So this raised all sorts of questions and confusion. And here's another one where the yellow line is where the solar flare went off, and the different color lines show the Parker spiral connection points to the different observing spacecraft. You can see that the stereo A is red, stereo B is blue, and green is at Earth as ACE. And so you can see that the green and the blue onsets are almost the same. They're almost on top of each other. Stereo A, red, which is on the opposite side of the sun, is delayed, but there's still an enhancement. And so the question is how is this happening? How are they getting all the way around the sun like this? This is for protons. And so you might imagine that the energetic ions could do this a little easier than electrons, because their gyro radii are so much larger. And even with the electrons, you see here, they're managing to do this as well. They're jumping all over the place. So yeah, and then there was this X-ray emission from GOES that they observed as well, low down. So finally, the solar wind, all of this stuff is happening in the background of really messy and interesting fluctuations. And I don't want to dwell too much on this, other than because this would be several talks alone. There's ion cyclotron waves, sometimes called proton cyclotron waves, or alphane ion cyclotron waves. The overall point is that they're left-hand or linearly polarized electromagnetic, and they propagate mostly transverse with the wave normal angle roughly 0. There's also kinetic alphane waves. These are a little sneakier because they can be left and right-hand polarized depending on the beta and the wave normal angle. They're also electromagnetic, but they have a wide range of wave normal angles. Magnetosonic whistlers or fast modes, also called electromagnetic lower hybrid waves. Again, right-hand polarized electromagnetic, delta B in phase with delta N, which is one of the ways you can distinguish them from kinetic alphane waves. And the wave normal angles are broad, but they tend to be within 20 to 60 degrees of the background field. And then there's the massive and confusing field of turbulence, which there's a nice review paper here on the kinetics or the multi-scale nature of the solar wind here. And it has lots of good references for people interested in turbulence. And I can also send people other references on turbulence if they're curious. And there's a lot more stuff going on all the way up to the plasma frequency and beyond. So we have radio waves and things like this. So all of these transient events, the particle stuff, the energetic particle stuff, and then the thermal particle stuff I talked about earlier are all washing through all of this in a sea of electromagnetic fluctuations. And so because these types of fluctuations are occurring all throughout the solar wind, and because they occur quite often, that's one of the many reasons why I'm always confused whenever we see any evidence of collisionality or things like this in the solar wind. So to summarize, the things I want people to take away are that, one, that the solar wind is not in thermodynamic or thermal equilibrium. It's commonly split into fast and slow solar wind, where fast is hotter and has a larger temperature, more anisotropies, and more tenuous. Slow tends to be more collisional, but even so, the collision rates tend to be less than 1 per day. So like I said, it's really surprising that we see evidence of collisionality. I just think that's really interesting. The CMEs versus CIRs. So the CMEs, when they generate effects in the magnetosphere, they tend to generate larger DST, so larger geomagnetic storms. They have a smaller relativistic electron enhancement, and sometimes they generate ground-induced currents, reformation of the radiation belts, and SEPs. The CIR or SIRs, they have a weaker DST response, but they tend to generate more severe relativistic electron enhancements. They tend not to cause reformation of the radiation belts or ground-induced currents. And SEPs is less clear, at least to me, and if there's SEP, CIR people on, they can probably correct me on this, but I think there's some debate about the role of SEPs with CIRs. I think there's studies on helium-3 to 4 abundance ratios in CIRs, but I think this is kind of one of these areas where the nuances got rather weedy very quick. The solar energetic particles, there's gradual versus impulsive. Graduals are almost all associated with some sort of ICME. They have longer durations, broad spatial extent, smaller abundance variations. Impulsives are often blatant on flares, but they rarely, if ever, see gamma ray emissions in the low corona. There's no evidence of nuclear processes. That is, they don't see lithium, beryllium, boron, or deuterium or tritium. There's a 1,000-fold increase in helium-3 to 4 abundance ratio, though helium-3 is not a nuclear reaction product, and sometimes associated with smaller, slower, and very narrow CMEs. So that's it. Thanks.
Thank you, Lynn. We have several questions for you. So I'll start. I'll just try to cover each of them one by one. Okay. And if there is if I'm asking the questions, I mean, if the person who has asked the question, if they feel that I have not framed it correctly, then they can maybe put it in the chat. So I'll start with the first question. First question was, by Ihua Zheng. Ihua wants to know that how do the statistical results on solar wind plasma properties compare to the previously published results, if there are any?
The previous what?
Yes, previous published results.
Oh, I actually did this study that's listed down here because I was at a APS meeting, and Justin Casper gave a talk on alpha to proton temperature ratio stuff and was mentioning 9 cyclotron waves and a bunch of other cool stuff, and it made me think. I was like, well, has anyone actually done a study on the electron to ion temperature ratio? Because I often see the value quoted, but I rarely see an actual reference or anything that's done a long-term statistical study. So the closest thing to a long-term study was by, I want to say, Newberry in the 90s. But they only used like 18 months of data. So that there wasn't much long-term statistical data. A lot of it was either case studies or anecdotal references. So.
Okay. So, have you compared your results with that? I mean, that's what you want to know. How?
Yes, I did. So I actually at the end, if you go and grab this paper, it's open access, so you don't need a license or anything. At one of the appendices, I have a list of dozens of different studies that were done prior to mine and what they found compared to mine. Okay. Yeah. Please, here.
Yeah, this is Iwa. I just want to say thank you. Yeah, it's very strange that there are no published work on this. Statistical properties. I thought that the people would done something using ACE data.
The problem is that measuring the electrons is really difficult. Actually getting the electron distributions nailed down is really difficult. It's not a trivial thing. And if you don't have the spacecraft potential measured properly, you don't have the instrument calibrated properly, and it's not really finely resolved at low energies, you'll miss most of the properties of the core of the solar wind. So
okay,
it's a difficult thing to do. So that's part of the reason why it wasn't done before.
Okay, great, thank you.
Okay, so the second question is from Vishwajit Oja. Vishwajit wants to know about the energy transport in the solar wind. So he wants to know, since there are several waves generated in the solar wind, so this energy transport is that dominated by the waves generated in the solar wind or the magnetic field frozen in plasma?
Oh, so you're talking about transport of SEPs and things like this, I assume. The diffusion that I mentioned earlier that affects the transport, I think I have it here. This type of thing has to be some sort of cross-field diffusion, and the typical approach to handle this is to discuss it in terms of turbulence. And so they'll talk about just a cascade of energy from large to small scales, and then they impose this on some simulation box, and then try to see if they can get particles to migrate far enough across the field to match the observations. if you have a beam of particles that are shooting out along the magnetic field, that will be inherently unstable and will generate all sorts of different types of electromagnetic waves from high frequency down to lower frequencies. And the types of waves that are radiated depends on the type of beam and the beam properties. And all of this is going to be, yes, will be dominated by electromagnetic fluctuations, not by particle collisions. So, because these are so energetic that the particle collision times would be incredibly small.
Mm-hmm. Okay. Okay, so we'll move on to the next question. Next question is from Kyle Murphy. Kyle would like to know if it is possible with new observations like from Parker Solar Probe to determine if and where the collisions occur.
Yeah, so that's actually one of the active projects people are working on with Parker Solar Probe is trying to trace the evolution of the different populations from inner heliosphere out to 1AU and beyond. And so the trick is actually getting really good measurements because like I said earlier, the electron distributions are hard to measure, and the Parker measurements are even more impressive because they have this huge heat shield in the way, and yet they still manage to get really good electron distributions. One of the things that they're finding that I find quite bizarre is that even at 30 solar radii, which is inside the orbit of Mercury, I think, so 29, 30 solar radii, the electron distribution is very different than what you see at 1AU. The electron distribution is almost entirely core electrons and a little bit of straw, but there's almost no halo. And so at 1AU, the halo tends to dominate in number density over the straw. And so the distribution, even in that short distance, has already evolved quite a bit. And the only thing I could think of that I could actually scatter the straw fast enough to do that would be waves, not particles. So and the other thing they want to do with SEPs with Parker is look at try to disentangle the local acceleration versus transport effects. And so they want to look at magnetic conjunction events between Parker and solar orbiter and wind, ACE, and stereo.
Okay. So the next question is from Samuel Hart. Samuel wants to know, like, considering the relative abundances, why would the alpha to alpha collision rate be higher than the alpha to proton collisions?
That's a good question. I think it's because the temperature is so much lower for the alphas in the slower wind, whereas and the other thing to be careful of is these collision rates are not symmetric. So if I change the alpha to proton, the order of the subscripts here, these rates change dramatically, and so it's the RMS thermal speed between the two. So I think one of the reasons is there's a charge dependence in the components here. So you have your charge components. So there's a factor of 4 difference there. You look at the alpha here, the normalization constant here, it's 64, whereas the proton alpha is only 8. So it's a factor of 8 larger. And then there's some other factors that play into this. So the mass ratio is larger, things like this. But that's an interesting question. I hadn't noticed that before.
Okay. Mm-hmm. Okay, so actually Samuel Hart is not right. He is not here. He has asked this question like via the YouTube video. So maybe he'll be listening there.
Okay.
Yeah. So could you just move on to the slide 21? So the next question is from Selva Kumaran, and he is asking, like, how does this co-rotating interaction region forms a magnetic structure like we see in the ICMEs to produce like different kinds of storms, like minor, moderate, or major storms?
How does it form magnetic structure?
Yes.
So again, this is so a little backstory. So when I was reading up on this stuff, I was I was kind of amazed at the amount of detail in it, like the number of different details for each of these different transients, and it became so overwhelming that I realized if I tried to include all of this stuff and actually discuss all of it, people would just fall asleep and they wouldn't listen to what I was saying. The CIRs and SIRs do not, as far as I know, generate have signatures looking like flux ropes or magnetic clouds. They don't have the slow rotation and stuff like this. This is not to say that flux ropes cannot be within them. It's just that there isn't so far as I know, the 1 or 2 day rotation of the magnetic field with a slow variation and that you see in CMEs. So I don't think that's necessarily what causes the geomagnetic storms. I think that's just a magnetic field orientation and the shock impacting the magnetosphere. And Joe or Mick would have a much better response than that for the magnetospheric response on this. But I'm fairly confident they do not have the same magnetic structure as CMEs.
Okay. Okay. So the next question is from Drew Turner. Drew would like to know what are the leading theories on why impulsive SEP events result in an increase in He3 production? And what about deuterium and tritium?
So why is there the 1,000-fold increase in the helium-3 to helium-4 abundance? So the helium-3 is in much larger abundances in the solar corona, and so the argument is that the acceleration site is lower in the corona for impulsive events than the gradual SEPs, I think, and so you're getting more solar material or coronal material coming out, which is also, I think, why you get larger abundance variations in impulsive events versus gradual events. I think that's, and the deuterium and tritium comment was made by in Don Ream's book here, that I have cited down here. He was rather adamant about going into detail about why well, not why, but that we do not see things like deuterium, tritium, lithium, beryllium, and boron in the impulsive events when we look at the ion composition, because if this was due to something like a solar flare where you have photons impacting the chromosphere and the photosphere, we'll often see gamma ray line emissions due to nuclear reactions like fission and things like this. And so the idea would be that you should see some of these nuclear products coming out from those regions, but they apparently don't. And so he went into great detail explaining what they do and do not see, and they often don't see the gamma ray lines low in the corona, which would be associated with these generating these nuclear products.
Okay.
But again, I'm not entirely sure this is settled. I think there are some SEP people online that might wish to argue about that. So I was kind of surprised at how much debate there is in the SEP community on this stuff. So.
Mm-hmm. Okay. Okay, so the next question is from Ankush Bhaskar. Ankush would like to know if the complex magnetic topology surrounding the SEP region can explain far side SEP observations.
Oh, so he's wondering if if an event goes off here and there's a really messy tangle of magnetic fields, could those possibly connect to all these different regions around? I have no idea. The answer is probably somewhere between yes and maybe and no.
Okay. Okay. So could you just move on to the slide 15?
15.
Yeah.
Yeah.
Okay, so next question is from Vishwajit Oja. He would like to know why there is a bump-like structure in panel E, that is for protons, and for H alpha,
Mm-hmm.
and which is missing in the slow solar wind.
Yeah, that was actually a question we asked in our paper. It's not entirely clear. The bulk, I think the this is the main part of the population of the fast solar wind, just showing that the fast solar wind is hotter for the protons. This tail is likely due to a couple of things, and one of them I think is related to what I distinguish as fast and slow solar wind. Like I said earlier, using the speed as the separation point is not sufficient to separate fast from slow when you're talking about the source region, whether or not it's a streamer or a coronal hole. And I think I'm getting what are effectively slow solar wind particles in some of this population, because it's not really the coronal hole source region. So I think that's part of that. This bump over here for the alpha particles, I'm not sure about. I'm not really sure if this is a similar type of a feature where the bump is the main population and this tail to the left is mixtures of the different solar wind sources. So slow solar wind population sneaking into my statistics.
Okay. Okay. So the next one is from Anil Raghav. And this is a more general question, like what is the cause of solar wind particle ejection out of corona?
What is the cause of the solar wind ejection?
Yeah, out of corona.
You mean the acceleration of the solar wind?
Mm-hmm.
I think that's a topic of active research, and that's why they launched Solar Probe. I'm not sure there's a simple answer to that.
That's right.
I mean, there's the cartoon picture that I know of is there's an ambipolar field that sets up because the electrons have a higher thermal speed than the ions, so they can generally escape the gravity well of the sun. They start pulling out ions, and the tricky part about this is that you have to be careful how you set this up, because you can set stuff up in that way with that ambipolar field, and you eventually reach an equilibrium where you don't get a supersonic solar wind, and so there has to be an additional acceleration or some other source there to help that out, because otherwise you'll just reach kind of an electrostatic equilibrium, and you won't actually get the supersonic wind. So this is stemming from what are called the exospheric models, I think.
Mm-hmm.
And if there's any exospheric model people online, they would know much more about this than I do.
Okay. Okay, so the next question is from Prasir. Prasir would like to know if there is a case study work or something like that which model the global detection of SEP, like in slides 27 and 28.
That model this? I think ever since they've observed these, they've been trying to figure out how to model this and how to get enough diffusion across the fields to observe this. I'm not sure of the current status on that, whether or not they've actively been able to explain it. I think that it's still kind of a source of debate, because I listened to a talk by Christina Cohen, and she was joking about how prior to stereo, they thought they understood impulsive and gradual events, and they thought they had this figured out. And then after stereo launched, and they started to see these huge longitudinal observations, and then they started noticing differences in the flux versus time profiles, suggesting transport effects. It reignited their curiosity and their interest in the field, because it raised so many questions. So I'm not sure if there's a clean or clear answer on this, and I know people are actively working on this, but I don't know what the status of that is.
Oh. Mm-hmm. Okay.
That is, I don't know what the status, like, have they made a conclusion yet? I know people have made arguments that turbulence can do this, and others have argued that certain types of waves, and some have argued that the field geometry, like the previous question asked, is a possible source. So
okay. Okay. So we'll move on to the next question. That's by Jason Dead. Jason would like to know if, have you integrated over the collision angle to see what total collisionality is obtained?
So there's a whole mountain of nuance involved in particle collision. So the funny thing is if you go through the derivation of this version of the collision frequency, like your question suggests, it only assumes 90-degree deflections, which is missing a lot of deflections, right? There's small angle collisions. Brent Randall's done some work on this, looking at how much of an effect it would have if you added small angle collisions, and it's surprisingly not that big of a difference from the 90-degree deflections. And but that's not the real issue. The real issue is that this is just a two particle collision frequency. The real way to handle this is actually have an n particle collision frequency. And if you've ever done the math for just getting the two particle, it's messy. You try to include a third particle, it gets really tiresome. And I don't know if anyone's been brave enough to do four particles by hand, but you have to consider the effects of all the particles within the biosphere and this type of thing, and it's not an easy calculation to do. So I think if you wanted to do this properly, you'd have to do it with something similar to like a PIC simulation or just an n-body problem, and actually have the Coulomb fields interact.
Okay. Yeah. Okay. So the next question is from Zubair Sheikh. So Zubair wants to know, have you considered the electrostatic waves in both slow and fast solar wind while calculating these collision rates?
Yeah, so that's why I included the ion acoustic collision frequency as a point of comparison. In fact, in the paper, I actually go through multiple different versions of this collision frequency where in one case, I just have the waves on 100% of the time, and I pick some amplitude. In another case, I consider the actual possible occurrence rate depending on the electron to ion temperature ratio and the occurrence rate of current sheets, because these ion acoustic waves tend to cluster around current sheets. So things like rotational discontinuities or tangential discontinuities or shock waves and things like this. Anything that has a large current, that you see the currents radiate like antennas, and the ion acoustic waves cluster around them. So I changed the probability of occurrence, and even if I do use my most conservative estimates, the collision rates are still significantly higher for the electrostatic ion acoustic waves than they are for the binary particle collisions. And that's only including one wave mode. There's also Whistler modes, there's fast magnetosonic Whistler modes, there's kinetic Gelfand waves. So
right. Okay, so the next question is from Yogesh, and Yogesh would like to know why we measure abundance ratios like He3 by He4. That's the ratio of He3 by He4. Why not the variation of only He3?
Because it's with particle detectors that measure mass per charge and try to distinguish mass constituents. It tends to be, the way they're set up, it tends to be easier to measure ratios of different populations. So like 06 to 05, 06 plus to 05 plus, it's easier to measure that ratio than it is to measure the individual populations alone. And since the abundance of helium-3 is so low in general, it tends to be very difficult to measure that population isolated from helium-4. And there's also limitations on the mass resolution and energy resolution and things like this.
Okay. Okay. Next question is from Judy Carpen. Judy would like to know how can you distinguish between the initial coronal properties of the wind and transport effects leading to observed properties at 1 AU? Seems like
yes,
all
good
these
question.
measurements are at 1 AU. Yeah.
That's an excellent question. So Ben Maruka actually did a study where he tried to take an observation at 1 AU and transport it back in time to the corona to see how things like this would change. So he was looking at specifically the alpha to proton temperature ratio, and he tried to consider how the collision rates and the collision cross sections, things like this, would change as you move closer to the sun. And the collision rates in general that tend to go up quite a bit as you get closer and closer to the sun, and they rise very quickly once you get into the corona and chromosphere. Once you get into the low chromosphere, they completely dominate. But the people have done this, and they think part of the reason for instance, for this bimodal feature is due in part to transport effects, and it's also there's also models done with the wave interactions where they have like fast magnetosonic waves interacting, and that can, in addition to ion cyclotron waves, they can generate this bimodal feature as well.
Okay. Okay, so actually we are out of time, so I guess we will end our question sessions here. I don't see many questions now. Okay, yeah, I guess we can end here. So thank you, Lynn, for your time. Yep.
Yes, thank you, Lynn, for the great presentation. Especially thank you for all the references within the presentation. I think that'll be a really big resource for a number of people.
Yeah, hopefully they can find stuff. And if they can't, at the very least, my 2018 paper has tons of references in it. I think it had like almost 200. So if you want to look up studies on thermal particle populations in the solar wind, that's great. The paper by Don Reams has a ton of references as well, and then the references within the references as usual. So.
Excellent, great. And thank you, Remya, for moderating this week. Next week, we have Heli Hedela, and she'll be discussing the bow shock and the foreshock. And so we hope to see everyone next week as well. Have a good week.
Yeah, thank you all.